All right, tomorrow we will have our last test. So we need to talk about what's going to be on that test. So what kind of things did we learn about in this chapter?
Black hole.
We learned about black holes, yep. Stars. Supernovas.
Black holes.
Okay. Yeah. We didn't really get to dark matter. I may talk about that a little bit after the test, but I decided to kind of cut things off with black holes. So it was good to have it on the vocabulary quiz, so at least you've kind of seen that before, but it isn't going to be on the actual test. So mostly we're talking about stars, right? Because all that other stuff that you guys just threw out, supernovas, black holes, all that kind of stuff, deals with stars. So what kind of things do we know about stars? Yes, Alex. Okay, they can come in different colors. What do the colors correspond to? So the colors come from the temperatures, and that comes from what? The size. So, what kind of color stars could we find out there?
Blue.
Okay, white / yellow. We've got blue ones, and we've got red ones.
What about violet?
No, not really. Right? No stars really get hot enough that they are able to give off purple light. Just don't find stars that big. So those are kind of the main colors that we see. Our star is technically actually white, our sun. It looks more yellowish just because some of the blue gets scattered out as the light comes in. But we can kind of call yellow and white the same category. Yes?
So, when like the blue stars, when they explode, can they give off like a purple light?
They're going to give off lots of different wavelengths, so yeah, there's going to be purple light mixed in there because there's so many other wavelengths, so it's going to look white. Okay? All right, now, as far as temperature goes, how do these things correspond? Which would be the hottest? Blue. Which would be the coolest? Red. Okay, now remember, these things are relative. Red stars are still really, really hot compared to Earth temperatures. Compared to the other stars, they are the coolest. And so white and yellow will say medium.
So
Okay.
if a star was close enough to us, it like set the Earth on fire?
Yeah, I mean, yeah, if you got it close enough, the heat coming off, the energy coming off would raise the temperatures enough that it would, I mean, set the Earth on fire. To be on fire, it has to be made out of carbon, so it would burn all of that stuff off, and then it would just melt the rock.
In certain places, there actually roads lead up. And like people, like when they walk, their sandals get stuck to it. They're watching it on streets.
Okay. Yes, Casey. Yes.
How do you feel?
All right. How do the sizes correspond? Which of these would be the biggest stars?
The white and yellow.
Well,
The blue ones.
the blue ones. Okay. And remember, we should put this here, because usually when we think of size, we think of volume. But what are we usually talking about when we're talking about stars?
Mass.
Mass. So, oops. What we want to put here for blue is actually the biggest. Which ones are going to be the smallest?
White, yellow, red.
The red. And so the white, yellow ones are medium. Okay, I'm going to add one more category on over here. Lifetime. What would lifetime mean?
How long they live?
How long they live? How long they last? So which of these are going to last longest?
Red.
The red. And which ones are the shortest?
Blue.
And which ones, well, medium.
Everything's
Right.
medium with them.
Yeah, our star is an average star. That's medium lifetime, medium temperature. Medium mass. It comes very typically. What's that?
Nothing. Do you want it to?
Now, we didn't, I mean, I kind of alluded to this in a few cases, but I don't know that I expressly talked about it. I do want to kind of throw this in here right now, though. Let's throw in a category right here, since I sort of ran out of room over there. You can add it to the end if you have room. Let's put rarity. Blue is the rarest, right? Red is the most common.
Let me guess. The normal one is normal.
Medium. So if you look at all the stars out there in the galaxy, most of the stars you find will be the red, coolest ones. There'll be a certain number of the white and yellow stars, but there's very few of the actual blue ones. Okay. So that kind of categorizes the different types of stars. What actually happens in a star? How do they make their light? Right. The light comes from nuclear fusion. Oh, sorry. Did I get ahead of you? Need me to go back up for a minute?
What is that? The red word?
I, the red and the blue.
The red word.
This one?
No, yeah.
This one?
Yeah.
This one?
Yeah.
Rarest. It's the rarest one. So, if you looked at, say, just 1,000 random stars, you would see probably, well, we'll just do percentages. Probably 80% of those would be red, 15% would be the white, yellow, and only about 5%. That changes a little bit. Okay, anyway. So the light and the heat that they produce all comes from nuclear fusion. What is nuclear fusion? David, what happens in nuclear fusion?
So the star is hot enough for atoms instead of bounce off.
Okay. That's good, but let's be more specific. What are combining and what are we making? Alyssa?
The gravity is so strong that the hydrogen atoms come together and make helium.
Okay, so the gravity forces hydrogen together to make helium. This would use the atomic symbols there. That. Okay, why doesn't that happen here on Earth?
Like a star. Because the gravity isn't pulling so hard on them.
Right, gravity's not strong enough. Gravity's not strong enough here on Earth. Gravity's not strong enough on Jupiter. It is more strong on Jupiter, but it's not quite strong enough. You got to get enough mass that the gravity is strong enough to be able to force those hydrogen atoms.
Do you know what happened if we shot water into Jupiter with a drone mass in it?
Yes. And if you gave it enough extra mass, it would start to fuse and become a star. So, theoretically, you could turn Jupiter into a star, but practically, the energy it would take, there's no way you'd be able to actually cut it. Yes? Forces. Sorry. Gravity forces hydrogen together to make helium. Yes? Casey.
But couldn't you basically launch the rocket so like when it does burn out, it could just drive right into it?
Yeah, but if you took every single missile on the face of this planet, the mass of those wouldn't be significant compared to the mass of Jupiter. So that's what I'm saying. In a practical effect, it's not really feasible. Okay, now here's the thing. This happens in all stars. Every single star out there, whether it's a tiny little red one or a huge blue one, there is some hydrogen that's getting forced together to make helium. But as you get bigger, other elements can be made. So as the stars get bigger and bigger, we can make larger elements. Right, and so kind of on the lower end of the spectrum, we can make up through carbon. So let's say lithium to carbon.
What about the iron?
Just a minute. So that's kind of in the medium type stars. When our star becomes a red giant, there will be some processes where our star will actually be able to make carbon. Of course, we know it has to make carbon because it's going to end up as a white dwarf. That's what a white dwarf is. It's just a big chunk of carbon. Okay, so these are kind of the medium stars here. And in the really big stars, we can make from, let's see what's after carbon. We get nitrogen, right? Nitrogen to iron. Okay, and remember, in the actual stars, no other elements can be made. Iron is the cutoff point. How do we get those other elements?
They belong.
Alyssa?
From the supernova, the explosion creates
Okay, so here, these big stars that are able to make up to nitrogen, when they go supernova, then they can make all other elements. So technically the big stars kind of make everything, but they can only make up to iron during their normal lifetime. It's not until they explode in that supernova explosion and die that they are able to make elements bigger.
So this right here is the star.
Yeah, I'm a star. Everything did.
Your left hand is then from a different star than your right hand. What?
They
Yeah,
would be
that's
like relative.
This hand.
the carbon in that hand technically could have come from a different star, supernova exploded their star. Probably a supernova exploded from the one in your left hand. As far as how that all works out, I guess I'm not exactly sure. Okay, now listen. We need to talk about the end state of stars. Because there's some different things that can happen. Okay, what do low mass stars become after they die? A white dwarf. So how would we describe a white dwarf? What do you think, David? Yes, David? Okay, good. Good. There's no nuclear fusion left. So the white dwarf, no fusion. Okay, how else would we describe it? David, keep going. Right? Really dense. How else would we describe it? Michael?
Going down.
What's that?
Going down.
It's cooling down. Good. Okay. Emily? Yeah, okay. We can say about the size of the Earth. Casey?
Giant ball of carbon.
Made of carbon. Nope. Yeah, I think that's pretty good as far as white dwarfs go.
Oh, I got one more. Discriminator.
Sorry. So that's low mass stars. What? What's that? Thank you.
Oh my god.
I don't think I'm gonna write that up there, but thanks for.
I just had to state the obvious.
Okay, when this high mass star, after it goes supernova, what's going to be left behind?
A neutron star.
Okay, a neutron star or a
Black hole.
black hole. So we're gonna look at black holes second. Look at the neutron stars first. So we'll kind of put an arrow down here. So let's describe neutron stars. What would we say as far as a neutron star goes? What was that?
They're like packed down. Hey.
Okay, packed down and tiny. How tiny?
I forgot.
Anybody?
Guys, that's his Earth. Mercury. About the size of New York City.
Yeah, about the size of a city.
Yeah, that.
Okay, so they're much smaller than a white dwarf, but how does their mass compare?
Very, very high.
A lot more mass than the white dwarf.
They're more compact.
Right, they're more compact, which means they have very high density. Okay, remember we talked about how a spoonful of it would weigh as much as Mount Everest.
Yes. Oh, hotter.
They still, I mean, like a white dwarf, they're still cooling down, so there's a lot of energy that's coming out. If you were to go right to the surface of one, yeah. Okay? And remember, the reason we call it a neutron star is because it's made of?
Neutrons.
Why is it made of only neutrons?
Because it's getting compact, and the protons are electrons.
Right.
They're becoming less slowly.
So the gravity is able to combine protons and electrons. That's why it is so dense. No space between the atoms. Yes.
Once like something like this dense.
That's a good question. So, to be able to undo it, really all you have to do is to take that stuff and spread it far enough apart that the gravity is not pulling it together that hard. Right? So it kind of do it on its own if you can separate it apart. Now, what force would be able to do that? I don't know. Probably nothing. You would have to have, okay, two different things that come to mind. Number one, if you have a collision between a couple neutron stars, chunks of them may fly off and then they would be able to kind of expand. So that would be one thing. Another case would be where it comes close enough to a black hole that it kind of rips it to pieces, and some of the pieces of the neutron star don't fall into the black hole. They get
Or if there were like two,
Do what?
like black holes.
And it was in the middle. Okay. Yeah, maybe. I don't know, Trace. Okay, so that's neutron stars. Let's talk about black holes.
Basically, we gotta talk about spaghettification.
Okay. Let's talk about the actual features of black holes first. Why do we call them black holes?
Because there's no escape of light.
Right. Light can't escape. All right. Why can't light escape? Austin.
Gravity is so strong.
Gravity is so strong. So these have extremely high gravity. Let's write this down, even though it probably doesn't make a whole lot of sense to you. As far as the density goes, we say it has infinite density.
Why didn't you just write the infinity sign?
Because I didn't. Okay, now, we had a couple different terms that we talked about in relation to black holes. I'd like to throw out one of those. Scanner? No? No ideas? Not spaghettification, but a couple different terms as far as the structure of black holes and how they're made. Alyssa, you got one?
There's a sphere, and they have. We don't know anything after the.
Okay, yeah, that's not. Maybe I'm not being clear. Oh, Casey, you got an idea? Okay, event horizon is
Yeah,
one
I
of
was
them.
trying to think of that one.
All right, let's focus here. What is the event horizon? Trace?
It's not like the center of the black hole.
No, not the center.
No.
David?
That's how well like it is when it gets started.
Nope. The other one. Emily?
Like this part where it starts. Like the part where you can't escape.
Where what can't escape?
Light.
Right. So the event horizon is the place where light is doomed.
That's all we know how far it is. Other than that, no.
Right. And beyond this point, we have no idea what the black hole is like. So beyond,
There's nobody in somebody.
we don't know.
Once you get sucked in, or not sucked in, once you get pulled in, you don't come back.
What happens to the event horizon if a black hole pulls in, say, a star?
Spaghettification.
What happens to the actual event horizon?
If there's like a flash,
Ellie?
it shoots something out.
Well, okay, that's if it passes in front of it, then yeah, then it'll bend the light. I'm saying,
It stretches. Yeah, I don't.
so that's what happens to the actual material, yeah, we'll get to that in a minute. But what happens to the event horizon if the black hole pulls something in and gains more mass? Easy.
It like expands.
Yeah, it gets bigger. So as objects get pulled in, as the black hole gains more mass, the event horizon will actually grow. So when we talk about black holes kind of eating things, and the event horizon grows as mass increases. And I know I just briefly mentioned that yesterday. Maybe it kind of got by you guys. That is absolutely true. It's not a euphemism at all. Absolutely does. Okay? So that's one term. You better remember the other term.
Nightmare.
Spaghettification.
Fight you, right?
Yes. Not just the child radius. The Schwarzschild radius.
I don't have. How do you properly say Arnold Schwarzenegger?
So, Trace, what is the Schwarzschild radius?
It's like what has to squeeze down into that radius for it to collapse.
Right. So it's the size that an object would have to get compacted to become a black hole.
Very smart. Interesting, but I don't think
Now, what kind of objects have a Schwarzschild radius?
Everything and anything.
Everything. All objects have a Schwarzschild radius. Listen. Listen. How come all objects don't become black holes? Listen.
it needs to get pulled in to be a black hole. It needs to be crushed right enough.
Okay.
Squeezed it.
Okay.
There's some
Still doesn't quite answer the question, though.
very
Right.
small. Not enough mass. I got it, mister.
Austin, what?
What happens is it has to have enough, like a lot of gravity, and it needs to have more force. No one thinks it's unification,
Right.
but like there needs to be more gravity pulling on it, so that when you're on one spot, you're gonna feel more gravity and it's gonna pull you down.
Okay. Let's stop you there.
Yeah.
So the point is, the only force that can get strong enough to pull things into beyond the Schwarzschild radius is gravity, and gravity only gets strong enough if you have enough mass. Okay? So only gravity can do this. But for gravity to be strong enough, you need lots of mass. And other than those biggest stars, there's nothing that has enough mass. Even in the biggest stars, the gravity is balanced until the star runs out of fuel and dies.
It's always a blast.
All right. Pretty much the last thing we have to talk about then is that wonderful term spaghettification.
I want some spaghetti.
Oh, yes. Sorry. That good? I work for you? Okay. I'm going a little fast, apparently. Pause for a couple seconds here, let people eat that up. We're almost done. We don't have long left.
I'm just stretching out my spaghetti noodles. Spreading out the ends. Stretch. And if you touch something, you're touching it. Let's pause. It's going.
All right. So we get through this. You guys just relax and listen. That's not relaxing or listening, Austin. Okay. Remember, what causes this thing that we call spaghettification comes from a difference in pull by the gravity. And that difference in pull is going to stretch objects. Austin, please. Okay, the next time I'm going to ask you to step in the hall. It's distracting. It's going to stretch objects to
Atom straight.
a line of atoms.
Because string theory.
Trace, what's going to happen to the material when it gets stretched into a line of atoms?
It's going to end up going in.
It will end up going in, that's true. What happens first?
It's like a big long.
Uh-huh. Anything else?
The light escapes.
Right.
Oh yeah, it makes a flash.
When it stretches into a line of atoms, that's going to heat it up and give off light. Okay? Last thing we have to talk about, how do black holes affect the area around them, close to them?
The polar.
Danica, you got something?
I don't want to say it.
I know it's
Why not? Huh?
Because she's gonna make a fool of herself on the internet.
Oh, nice. Leslie, it bends space and time. Okay? Now, what effects do we see when it bends space?
Light is a different scale.
What?
Different.
Leslie. Right. It changes the direction of light. What effects do we see when the black hole bends time? What effects do we see? Melissa?
We wouldn't see anything. We wouldn't see a difference unless there was somebody there and spent like 20 years there on Earth.
Yeah, so that's not really helpful at all. When it bends time, what we see is that time moves more slowly. Okay? Now, we have to remember that this happens for all objects of mass. It's just we tend to see we would see much more significant effects of it if we're close to a black hole. Being close to the Earth does slow time down a little bit compared to not being close to it, but it's such a small difference that we usually just kind of forget about it. Here it would be a very big difference. So time moves more slowly. Let's see. Okay, now listen.
So you just run out.
Listen. This test tomorrow is going to be slightly different than the test that we've taken.
In what way?
I would love to explain to you if you would shut your mouth long enough for me to.
You want to shut? You want to
So the test tomorrow, I've made up a bunch of questions, and I've went through and I've answered them. Some of those answers are going to be correct. Some of them will be incorrect. So tomorrow, and I will explain this all tomorrow to you in case you don't quite get it. But basically, you have to evaluate my answers. If you read my answer and you go, yeah, that explains it pretty well, you would put correct by it. Okay? If you read my answer and you're like, that's not how it works, then you need to say incorrect, and then you need to explain why my answer is incorrect and what the correct answer is.
We're getting graded on grading.
You're getting graded on how well you evaluate my answers, yes.